Good evening, everyone. I'm Prablin Kukreja. First of all, I want to ask, am I audible? Can someone write in the chat or unmute and okay. So, good evening, everyone. I'm Prablin Kukreja from PhD scholar from IIT Tirupati. So, we'll start our session, week 7 of a computer network session. We'll try to cover the whole transport layer along with the sockets part today. And as we discussed in the last lecture, we'll also do the programming as well today. So let's start. I'll have a quick recap of the last session for the continuity. Not the full recap, just the one where we left. Is my screen visible? Okay, thank you. Wait a second. So just have a quick revision. So we have studied about delayed acknowledgement, Nagel's algorithm. First of all, can someone tell me what is delayed acknowledgement? Just to see whether you guys remember or not, so that I can go ahead for the continuity. Yes, come on. Yes, guys. What is delayed acknowledgement? Can someone recap this, like delayed acknowledgement, Nagel's algorithm, Clark's algorithm? First of all, delayed acknowledgement and Nagel's algorithm, and why don't they go with each other? And then coming to the Sullivan-Rose syndrome. Can someone recap it very quickly? Yes. Am I audible clearly? As I'm not well, I can't speak loudly. Like I was thinking to postpone the session because I'm having the fever, but I thought, okay, let's go with the. Yes. Am I audible in the first place? Okay, thank you, Aman. Now, can someone tell me what is delayed acknowledgement and Nagel algorithm and why don't they go with each other? Just a quick recap.
So delayed acknowledgement is like waiting for packets. The receiver is waiting for packets, and then it is sending an acknowledgement.
And Nagel's algorithm?
So there is kind of a starvation. Either packet is not sent or packet is not received. Um,
Yes, yes, yes. So let's once again go through this. Like here, delayed acknowledgement is like the sender basically they are waiting for like up to suppose as they have written 500 milliseconds in hope for receiving more packets, so that and they're as the name suggests that they're delaying the acknowledgement. Okay, let the more data come and we'll send back the acknowledgement after more of the data will come after 500 milliseconds or so. Whereas Nagel's algorithm is like first it will send the first packet and hold the subsequent packets till until the previous packet is basically acknowledged. So what they are saying is until the first packet, I'll tell you here, what they are saying, the receiver is waiting for more data to come, whereas here the sender is saying, I'll send the first packet, I'll not send, send the first small packet, whatever it is. I'll not send more packets. I'll wait for the acknowledgement and send more packets. Till that time, more data will be get accumulated. So sender is waiting for the acknowledgement from the receiver, whereas the receiver is waiting for the more data to be sent by the sender. So that's why they don't go with each other. As I have written, when an acknowledgement will receive, till that time I will accumulate more packet. That is the main motive, intuition behind Nagel's algorithm. Whereas delayed acknowledgement is, I will wait for more packets, then we'll send the more acknowledgement. So that's why they don't go hand in hand with each other. Then we studied about the silly window syndrome. And suppose here we are sending 10 mbps, whereas the receiver is only 1 byte. Then what to do? How again we have to again the same problem is there, that sending we have to send in the small segments. And we don't want to send in the small segments, basically, to avoid the overhead, bandwidth, cost and all. So that is why we came up with the Clark solution. Whereas we studied that the Clark solution as well as the Nagel's algorithm, they are going hand by hand with each other. They are complementing each other. And suppose there is an suppose there is an exception that I want to send the data immediately rather than waiting. Then we have some emergency like flags available, that is like push flag, like I want to send it immediately. Some application is like that. And we can use in that case push flag rather than using this Clark's and Nagel's algorithm. So we have that part as well. And then we studied about the round RTT, retransmission timeout and all. Now can we were going to start with the Jacobson algorithm. That is where we ended. Can someone tell me what is this Jacobson algorithm in short? Yes, come on. Why it's used in the first place? Why we are using Jacobson algorithm before moving it to it? What we studied, okay, I missed some part. What we studied about transport layer RTT, retransmission time, what we studied about that?
So Jacobson is used to like determine RTT.
Yes. Why we have to determine RTT by Jacobson algorithm? Last time we studied about this transport layer and something about data link layer. Can you explain that?
So actually, if so, basically, it's about observing packet loss, and the thing is that I think after three times some duplicate acknowledgement is sent, so congestion is like congestion control kicks in. So something related to that.
Basically, I'll say if I am calculating round trip time of DLL, data link layer, then that's not that much variation is not there. But if I talk about please, can you mute yourself? Hmm. So if I talk about transport layer, the variation comes into picture because of, as you told, that congestion and various other factors as well. So that is why uh, the variation in dynamic data link layer variation is not high. So dynamics uh, like uh, are changing very less, whereas here there is significant deviation. So we have to come up with some approach, like Jacobson algorithm is an approach which is used to calculate retransmission time. Can someone explain me what is it like? What is Jacobson algorithm says? So basically, they are maintaining a variable called SRTT, which is smooth round trip time. As you know, round trip time is basically going and coming back, sending the data and receiving the acknowledgement. That whole time is basically called as round trip time. And if I talk about smooth round trip time, that is basically the best current estimate which can be calculated of round trip time. That is what smooth round trip time means, not something extra. So, uh, when this, I'll say when the segment is sent, timer basically it is started, and then we see that how much time it is taking for sending and receiving. That basically we are calling it as R. And SRTT, as per the definition, alpha SRTT plus 1 minus alpha R, whereas alpha is 7 by 8. This is a smoothing factor, or weight, like we say about weighted average or smoothing factors. That is what it is done by, like there's a whole research how they have like uh, uh, like how they have determined this alpha. So I'll not go into that deep. Basically how this alpha is calculated. Now till now everything is clear.
Yes, ma'am.
So if I talk about RTO, so basically even if we have RTT, then also round trip time, then also retransmission, or basically that RTO, basically it's difficult to retransmission timeout. It's basically non-trivial. It's difficult to calculate. If I talk about the initial implementation, it was like RTO is equal to 2SRTT. But with the experience, they showed that okay, this is not a, like we can't take a fixed value because RTT is basically fluctuating because of various factors. So we came up with RTT where variable, like RTT var, basically variation in the RTT, that is equal to beta. I'll come to the numerical. Don't worry if you're not able to understand. We'll again go through this. 1 minus beta SRTT minus R. And here the beta value is taken as 3 by 4. And then the RTO is calculated. That is SRTT plus 4 into RTT var. If I come into 4, then also I'll say that this is also a huge paper where they are saying that how 4 is basically selected here. And then this is how the RTO estimation goes on. So it's like the whole mathematical part, how basically they are calculating the retransmission time. So let's go to numerical, and then we'll go to each and every equation. I think so it will be clear. If it's not clear till now, it's fine. We'll go through the numerical and try to understand these. I think practically if we'll do that, it will be more clear. So suppose initial, I'll say estimates which are SRTT and RTT var. First of all, can you tell me what is this again from the starting? I'll start. What is SRTT? What is RTT var? Come on. Just to get an over, I'll get to know whether you are getting it or not, the concept. Yes, these are the initial estimates of RTT and okay, SRTT and RTT var. Can you tell me? Yes, come on.
SRTT is smoothed RTT, right? Yeah.
Oh. So basically, it's like smooth RTT and RTT var. As we saw that we'll have the variation, RTT variation somewhat. So that is why we are using RTT var. These are the initial values given to us. And as we have seen that alpha we'll use as 7 by 8 and beta we'll use as 3 by 4. These are the given values which they are using. Now, first, if I talk about first sequence, let's have the sequence of events, how this is happening, so that you can understand how the things actually happen. So first RTT measurement, let's do how much so 1 minute. So actual RTT, suppose, is 120 millisecond, and I'll come to it, don't worry. And new SRTT, as let's see the formula here, it's alpha SRTT plus 1 minus alpha R. So what is alpha? That is 7/8. SRTT, as we have seen, that it's 100 plus 1 minus alpha, that is 1 minus 7/8. What is it? 1/8. Sorry. And then we have R, which is the value of R is basically actual RTT, which was at that time, that is 120. Now coming to the equation again. So we have the alpha given, we have the beta given. Oh, so alpha, now we have to calculate SRTT. First thing is that whenever we are given with it, so how much is the smooth round trip time? So I'll calculate the actual round trip time, how much it was taking. Like 120 millisecond was actually it was taking to send and receive the data. And if I talk about new SRTT, so I'll take the value of the old. So initially we have taken, okay, let it be 100 millisecond arbitrary value, and alpha we know, and R, it was the same, how much actually it is taking from sending and receiving the data. Till now clear? Okay, Aman has answered it. It's 77.5. Let's see. I have also not solved. I'll solve it with you guys only. I'll not solve this question. Okay, let's see. So, okay. Okay, you are talking about this new SRTT. Is it like that, Aman? Or you are talking about...
New SRTT.
Okay, new SRTT. It's... are you sure? 1 minute. Calculator. Just in case if 700 divided by 8, it is 7.5 plus 120 divided by 8, that is 15. So it is 7.5 plus 15. It's 102.5. Yes, yes. In calculate. So now we come up with, okay, now SRTT, our first thing is okay, done. We have calculated SRTT. Now coming to RTT var, variable RTT. Now what is the formula of that? SRTT plus 4 into RTT. That. Oh, it's RT. Sorry. RTT where it's beta into RTT plus 1 minus beta. What is, okay, I'll write the formula first. 1 minus beta into beta RTT where plus 1 minus beta into SRTT minus R. So beta, as we are given with the beta, that is 3/4. RTT where that is 10 millisecond plus 1 minus beta, that is 1/4. And SRTT, it's 102.5, now only calculated, and 120. Can someone calculate the value and tell me? Yes, someone. I'll calculate. Okay. 11.875. Just for the checking. Oh, I'm sorry. Beta is basically here. Is it 3/4 or 1/4? Just hold on 1 minute. Fine. So 7.5. Are you sure? Should I write it like this only? So it's suppose 11.875. So here we come up with the first RTT measurement. Is it fine till now? Should I proceed? Now, similar way, I'll not do the rest one because of the lack of time. You can try with okay, I have to show you one thing about the currents algorithm. So I'll do this.
இல்ல ஐஐடியோட கிளாஸ் 6 to 8 மறந்துட்டேன் அவன் வந்தோன்னு.
Please mute yourself if you are not having any doubt or you don't want to answer anything because there's so much of disturbance. Okay, let's start again. Second RTT. Can someone solve second RTT? I'll tell you. Suppose here in second RTT, I have to tell you the actual RTT measurement is suppose 110 millisecond. These we are going very smooth without no retransmission. I'll tell you one. I have to introduce Kern's algorithm as well within this numerical, so that's why I'm going ahead. So can someone tell me what is new SRTT? Everything is given to you. Alpha SRTT plus 1 minus alpha into R. R value is given. Alpha value is with us 7/8. SRTT 102.5 plus 1/8 and R is 110. Yes, what's the answer? I'll check. Someone has written in the chat 150. New RTT. Is it new SRTT? Aman? I'll just check. Ah, 103.43. Absolutely correct, Sujan. Now, can you guys solve this new RTT where as well? Just doing it because I want to show you something. Okay, I think RTO I haven't calculated last time. Okay, new RTT where can you calculate it? It's like 4 into 11.875 plus 1/4 into 103.43 minus 110. Yes, someone can tell me the answer quickly. Yes, quick. Is it correct? Am I doing some mistake? Why you're not? It's modulus. Sujal, it's modulus, so it cannot be in minus. Yes, absolutely. Can you once check the calculation and everything? Is it fine? Should we proceed? Till now, any confusion with anyone? I've done one mistake. I forgot to calculate your RTO. It was the main thing which we have to calculate. So RTO is basically SRTT plus 4 into RTT. So what is SRTT in the first? SRTT here in the first one, not in the second one. SRTT was 102.5 plus 4 into 11.875. This was the main motive. I forgot that only. So what's the value? Only 1-2 students are solving. Please, I'll request everyone. Let's solve. And if you're not getting, I'll repeat it 10 times, but ask me. Make it as an interactive session. It shouldn't be like I am speaking and you are listening. Okay. New RTT where 1.54. Is it 1.54 or 10.54?
10.0.
Yes. Okay. And RTO value is 150 here. Is it like that? What is the previous RTO value? Is it previous RTO value you are telling, or the second one?
The calculated one.
We have done the first and second like RTT. First, we forgot to calculate.
Yes, the first one, 102.5 plus that
one.
one.
Okay, that's 150. Okay, and now coming to the second one of this. Let's be quick as we have to do socket programming as well today. And we are already going 1 week delay. I'll take one extra lecture as well, so that syllabus should be completed at the end. Yes, come on. Or should I solve? It's SRTT. What was SRTT? 103.43 plus 4 into, is it like that? 4 into RTT where? I'm just repeating it just because I have to show you in the third. Maybe I should have shown in the second. Okay, it's fine. Yes, come on. Simple calculation only I'm asking for. Hmm. 145.644. Yes, it's 625. Wait a second. Okay, approximately this only. Okay. Now coming to the third one. Now this is the main. Can someone tell me about the currents algorithm? Before going to the third one, I want to ask you, can someone tell me about the currents algorithm? Yes, come on. So Kern's algorithm says, before starting this third, I'll try to incorporate this Kern's algorithm here only. Check whether anyone has written in the chat. Okay. Used to handle RTT in case of lost packets. Absolutely correct. So how to handle, as you have said, this is used to handle the RTT in case of the lost packets, but how to handle? In Kern's algorithm, what does it say is that do not update any segment that has been retransmitted. So basically, whenever there is a retransmission, don't update any of the segment. Don't update the RTT value, anything. Just double them each. Like I'll show you what to do here. What do I mean by doubling them, and what do I mean by not updating them? So suppose like we have the third RTT measurement with the retransmission. I'll calculate the third RTT measurement. And suppose there is a retransmission, the segment is lost here and needs to be retransmitted. So what does it says? I do not update SRTT and RTT var based on the measurement. This is what the Kern's algorithm here says. And the other thing, the main thing, what it says is double RTO from last successful transmission. So I'll not calculate RTO. Just what I'll do, I'll double it from the last successful transmission. So what was my RTO here? It was around 145.644. Now what will be the RTO? It will be multiplied by 2. So what's it? What's the value? So 291.288 millisecond. What does it mean? It means wait for 291.288 millisecond retransmission time, like then only before retransmission. That is what we are calculating. The same way we can calculate for fourth and all. So this algorithm was just to show you how the timeout RTO values basically are calculated. Now I have also incorporated this Kern's algorithm so that you'll get the idea of this Kern's algorithm as well. Any doubt? Yes. Yes, come on. I'll repeat it again, the whole thing, if you are having any doubt. If you are clear, please give the thumbs up or write in the chat. It's clear and I can proceed. If you're not clear and you're having the doubt, please write in the chat that as well. At least give the feedback. Am I audible in the first place? Because I'm not receiving any feedback. Clear. What about others? Only one of you, is it clear? I'll wait for 2 minutes more so that if it's not clear also, it's fine. I'll repeat everything. It's fine, totally fine. Yes, come on. What about others? Okay, let's proceed. I hope so. I got only two clear. I hope so for everyone. It's clear. Yes. Okay, let's proceed. Just this was numerical, nothing else. Uh, a simple numerical. How we are taking, how we are updating the RTT values, how much we have to wait basically before the retransmission. That it was like for how much time we have to wait, how we have to calculate it, because in transport layer it's tough to determine. So they came up with the Jacobson algorithm where they calculated the RTT, which was not the simple RTT, which was the RTT variation, where they took some fact like beta, alpha and beta factors, weighted average type, and then they calculated RTT var, RTO, as well as SRTT, smoothing RTT, and then basically calculated this RTO. And in the case of when we have the retransmission, obviously we can't calculate it correctly. So that's why they just took the RTO value as double. That is what Khan's algorithm says. I hope so. It's clear. Now let's proceed. So we have the other types of timers like persistent TCP timer. So anyone can tell me about persistent TCP timer? I hope so you're listening to lectures as well. It's just a repetition of the lecture, what it's mentioned there as well. I just showed you the numerical so that you should be clear with the concepts, and I can give you more clarity. Okay, someone has written the chat. I think Aman. Probing packet if receiver send window size is equal to 0. Exactly. So what's that? Let's see. So as he has written, we have it's like probing a packet if the receiver window size is 0. So basically, in easy words, if I have to explain, if the sender sender receives 0 window size notification from receiver, what does it mean? It means that it cannot send more data. I'm done with it. I'm not having more space. Don't send more data. That is why I'm sending window size 0. I don't have any more space. But now the connection should remain alive, and the sender should check the receiver, like whether the window size has changed or not. That's why we are using this persistent timeout timer. Basically, the sender has received the 0 window size notification from the receiver, but however, it must ensure that connection remains alive. Why it wants that connection should remain alive? Any idea? If Windows 0 is sent, which means that receiver is not having more space. Now, why? What's the motive of checking that connection is alive? Any idea? Receiver has sent to the sender 0 window size. I don't have any space. Don't send more data. Now, why the sender is like, okay, I want to check again and again that I want to make this connection remaining alive. I don't want to end this connection. Yes. Yes. Come on. Just what's happening? Are you getting it? Why today's lecture is so so much like only one way lecture? Is it like what I am thinking, or is it actually happening like one way lecture only? If you're not able to understand, ask me multiple times, but don't be silent. What do you guys think? If sender is sending and receiver is saying, okay, I am sending 0 window size notification, what does it, and the sender wants that the connection should remain alive. Why the sender wants that the connection should remain alive? Any idea?
So that it can send more data whenever it receiver gives the free buffers.
Yes, simple. Like if I why the sender wants the connection alive, it was a very trivial one, simple one, that in order to check that the receiver's window size has changed, so that the as you have said that whenever it has free like space, it can send the data, basically in order to check receiver window size has changed or not. So basically to not close the connection, so that is why we are using this.
Ma'am, cannot hear you.
Am I audible now?
Yes, ma'am.
Wait a second. Maybe I am disconnected from my iPad. Wait a second. So, till what time I was audible? Like you heard about this keep alive timers and all?
No, ma'am.
Okay, okay. Wait a second then. Am I audible now? Am I audible now?
Yes, ma'am, but your voice is echoing.
What about now?
Same.
Wait a second. Is it fine now?
Yes.
Sorry for the disturbance. So, this persistent TCP timer, have you heard about, like, were you audible at that place? Like, I was audible at that place, or you haven't listened about that also? Can you tell me, like, when was you till what you have heard? Like,
Around keep alive, just after keep alive. Lost.
Persistent TCP timer is done. So keep alive timer.
Yes,
So
ma'am.
now can someone tell me in very short, what is keep alive timer? Like keep alive timer is like whenever the connection has been idle for very long duration, so close that connection. So that's basically keep alive timer. It's not much. Now I was talking about this AIMD and all. So what I was talking about, as we have done this AIMD, was it clear in the first hand? I hope so. I've explained in transport layer about that. So was it clear about that? AIMD is clear. So should I proceed and skip that AIMD part? Okay, Sudha, what's your question, ma'am? Is there any specific advantage or disadvantage of this? So basically, we are here calculating the how much time we should wait for before transmitting. These are all the timeout things before retransmitting the packet. How much time we should wait, that we have calculated through Jacobson algorithm, the RTO. If I talk about the persistent TCP timer, that was like if a zero window size notification is received, then it means that it cannot send more data. So how much time the connection should remain alive. So these are type of different timeouts. So, before that, like retransmission timeout or different types of timeout which are used in the transport layer. And here it was just the calculation of that RTO thing, after how much time we should retransmit. That is basically the specific advantage of that, basically the usage of that, rather than saying the advantage. So I hope so AIMD is clear. Should I skip that part, because I have already shown you the numerical part as well of the AIMD? I hope so that part is clear. I'm going to skip that. I have explained you in the transport layer, but as I told you, I thought that earlier that I'll show you the numerical here only, but then I thought, okay, at that time it was important to show you about the TCP, because you all were getting confused about that AIMD. So I thought that, okay, it was important to show you. Can someone just give me a quick overview of AIMD? Just a quick overview, like in 2 minutes. Yes. Just a 1 minute overview.
Ma'am, it is about to check the congestion control by uh, addition, increasing through additive power and then decreasing through multiplicative power, so that the congestion will be in control, and I mean, as per the rate of the packets, it will be maintained.
Yes, absolutely correct. On point. So first we start through slow start, which is basically a doubling, multiply by 2. And then once the congestion is received, we apply AIMD, congestion avoidance algorithm, where we are increasing by additively, whereas multiplicative decrease, which means that the threshold we are dividing by 2 and decreasing multiplicatively, and then going through again the same phase.
Yes.
Now, can someone tell me, this was the simple approach of the, this is the AIMD approach. Can someone tell me about this 3 duplicate, what do we do if we have 3 duplicate acknowledgement as a sign of congestion? What was the difference between the earlier one and now? Come on. Earlier also congestion was detected. Was the congestion detected through the 3 duplicate acknowledgement? We were getting the 3 duplicate acknowledgements?
In
Mhm.
previous case, it was RTO, so timeout was happening. We sent the packet.
Yes. Okay, wait a minute. So in previous case, the timeout was happening. So now in this case, 3 duplicate acknowledgements are there. Now what to do? Is it like we should apply the same AIMD approach, the slow start phase and then the AIMD? Yes, come on. Yes, can you tell me?
ఎవరం తినేవి తిన్నావు చక్రాలు అన్నాను
Please, can you mute yourself if you...
తినమని చెప్తున్నాను
Okay. Yes. Is it the same approach we should use when, okay, the congestion was detected earlier by the timeout method. Now it's detected through using three acknowledgement. We are getting the three duplicate acknowledgement, which means that there is the possibility that like congestion is there. So now, but the congestion is not that severe because we are not having the packet lost or so. Still, links are flowing off. So is it like we should use the same approach or some other approach? Yes, come on.
No,
Come.
I think we should use the same approach.
What about others? Okay. Aman is saying fast recovery. Absolutely correct. Actually, we should use a different approach, that is fast recovery approach. So let's see that how that fast recovery approach comes in, like how we have to do that. I'll go through the same algorithm, EIMD one, and we'll, rather than solving through EIMD, let's solve through this fast recovery so that it should be clear. Okay. Was there any doubt in this algorithm as we have done last time? Was it clear through AIMD method, or I should give you just a quick overview of that?
It's clear, ma'am.
So it was like we started with the I'll just go through just we started with the slow start phase 2 MSS, and then we multiplied by 2 as we are in the slow start phase. When we reached at the threshold, that is 8 MSS, we started increasing by 1, and when there was a timeout, now you can see that a timeout means that the congestion is there. Now we are having three duplicate acknowledgements. Here the timeout was there, so what we did, we like divide by 2, that is the threshold was changed, and then again we started with the congestion window, that is 2 MSS, and again we multiplied by 2, the threshold was changed to 5. So that's why we then obviously at the transmission 7th only we have to additively increase it. So we have to the question was till the 10th transmission what should be the window size, and we came to this 8. Now coming to the, if rather than timeout, I'll show you here only. Rather than timeout, let's have 3 duplicate acknowledgement. Any idea what will like as one of you, I think Aman, or I think so, he told that okay, it's like fast retransmit, fast recovery. So can you tell me about fast recovery as you have written? Okay, let's start. So transmission number 1, they're the same as it is. Like I start with 2 MSS. I hope so. In last lecture you have attended. I am assuming that. If you have not attended, you can check that on YouTube channel again. Go through it. We are in the slow start phase. 2 MSS multiplied by 2, that is 4 MSS. This is the same thing. Transmission number 2. Again multiplying by 8. Then transmission number 3. What was the threshold? 8 MSS. So we have hit the 8 MSS. Now additive increase, 8 plus 1 is equal to 9. Then transmission number 4, that is 9 plus 1 is equal to 10. This was the same. Now, as we saw that in transmission number 5, there was a timeout. Now, rather than being having a timeout, we have 3 duplicate acknowledgements. And which tell us that, okay, there is a congestion, but it is not that much severe. So we should use an approach called fast recovery. I'll come to that. Now, what does it say? It says that I'll start the window size, congestion window is equal to 10 MSS. Second. Now 10 divided by 2, that is 5 MSS. What was in the previous state? Again the same thing. 10 by 2, that is 5 MSS. Now what is the difference? Can someone tell me?
The window would be 5 plus 3.
How it is 5 plus 3? Can you tell me?
So 5 is the a threshold, new threshold.
Okay. Now rather than increasing by 1, what we are doing? We are increasing by 1, but what is this plus 3? Can you tell me?
Because of the 3 duplicate acknowledgements, dupex.
Yes. So basically that is basically 5 plus 3, that is 8 MSS. TCP does this because of 3 duplicate acknowledgement, implies that 3 MSS, I'll say, like of the data have left this network. That is why. And now wait a second. Now what will happen next? Yes, come on. Transmission number 6. Should I start from 2 MSS again? Like here we have started from 2 MSS. Should I go to the slow start phase again?
I don't think so.
Yes. Basically here, this is the difference. I want that. Okay. Again, maybe no one has asked me about the last problem which I have given you. Have you solved the last homework question? Okay. If you have solved and any doubt is there, please can you or you can solve in the next class. Please tell me at least. Again, I'll give you this transmission 6 to 10 as a homework. What should we do? Like whether we should start as 5 MSS, whether we should start from 2 MSS, and how it will be there. And what is this basically, why we are starting with the 5 MSS, and so I'll just give you as homework problem here. It's just okay. I'll tell you also here what we are doing is we are starting with the 5 MSS. We are not going to the slow start phase. I'll remember in the next class that I have to go with this thing again. And I want the answer. Okay, can someone tell me the answer? Do we get acknowledgement after transmission number 5? Transmission 5 is we are getting the 3 duplicate acknowledgement. That is what it's written there. Like here the timeout was 5 at transmission number 5. Now here 3 duplicate acknowledgements are at 5 path number 5. So how these things will be?
So we will exit this fast recovery once we get an acknowledgement for the missing one. Till then,
Like it's like till 5 MSS it's fine. I'm also thinking that it's like then we don't have to go with the slow start phase. We'll start with the congestion window size as 5 MSS rather than going to 2 MSS.
yes, ma'am.
So rather than going to 2 MSS, slow start phase again multiplying by 2, because it's not that where we'll not go to slow start phase because it's 3 duplicate acknowledgement means that the congestion here is not where the flow is going on for the other parties as for the other transmissions as well. So don't enter the slow start phase. That's the major difference. Just start from the this congestion window like 5 MSS here. I'll suggest this is my request to you. Please solve this question. Then we'll again go to I'll start the next lecture by this only. I'll remember that. Always forget these homework problems. So I'll start. I want that anyone should share the image next time and should explain what's the difference between, explain both AIMD and this TCP 10. Basically, three duplicate Renault's fast recovery, three duplicate acknowledgement. I want that someone should explain because it's a very important topic. Here, the key difference is we are not, I'm telling you the whole problem itself, whole answer itself. Here we are not, here we are going again to 2 MSS. Here we are not multiplying by 2 and all and then additively increasing. Here we are starting from that additive increase. We are not going to back to the slow start phase. That's the major difference. Is it clear?
Yes,
Should I
ma'am.
proceed? I hope so. These things are clear. Only slow
Yes,
start
ma'am.
phase is not there. I think that
Ma'am,
then it's trivial, like it's
I,
very simple only.
yes, ma'am.
So let's proceed.
Yes, ma'am. So I think because it is receiving the acknowledgements, so that means it has received the previous data. That's why the acknowledgement is there, and the data has been transmitted from the sender side. So maybe
Yes,
that's the
yes.
reason we shouldn't go for so slow start phase, because the flow has already been made when the congestion is over.
Basically, why we don't want to go to slow start phase, and again, we are doing this fast. The name itself is saying that fast recovery, because if we'll go to the step one in the slow start phase, we are going to that slow start as we have explain discussed in the last class as well. Slow start, the name suggests that we are starting from a very small value, though it's exponentially increasing, multiply by 2, which means that the congestion was very severe. That's why we have start through a very small value. Possibly the packets were lost, but here the congestion is not that severe. We are not sure that packets are lost or not. We are getting multiple acknowledgements, which means that we are in the doubt that maybe possibly packets are lost, but still links are flowing. We are not getting a timeout here. Like, okay, the time, like we are not getting the timeout here. We are only getting the 3 duplicate acknowledgement, which indicates congestion is not that severe. We shouldn't go again to a very small value for the starting. We should start from, we should do the fast recovery. That's why we are not going to the very small value, I'll say, again starting from the slow start phase. Is it clear?
Yes, ma'am.
I hope so. This concept is clear. Now coming to UDP part. Can someone tell me why UDP is used? Like we have discussed in many classes of this about UDP and TCP, and why UDP is used. What is the drawback in TCP, or what is the drawback in UDP in some applications? Why we use TCP? Why we use UDP? Can someone explain me?
Ma'am, UDP is generally fast as it is connectionless,
Mhm.
because it does not care about the ordering of the packets, or even whether they are getting properly delivered or not, because it will just simply transmit and try to get it to the receiver's end. So it is reliable for real-time processing, because at that time only getting the data transmitted is the only concern, rather than sequencing them or having them have proper congestion control or reliability check like the TCP. So
Yes,
that's why it is not so much slow or not so much complex.
absolutely correct. You have, I think you have covered all the points. So
Yes, ma'am.
basically, UDP as the main thing is like in TCP, it's basically time consuming, and some applications, I'll say some real time applications, for them it's very problematic situation. So that's why we come up with the UDP here. And why it's time consuming, there are many factors. If I talk about connection establishment, which means we have studied also about connection establishment, the three-way handshaking. It takes the time. What are the other times? Flow control. Basically, retransmission of the block. If flow control, we have to retransmit if there is a existing data. If I say about the congestion control, that also carries the overhead.
Ma'am, also do data timeouts.
Time, obviously this contains the timeouts only. I want to say, if I talk about congestion control, we are again AIMD, we are starting with a very slow start, slow phase to reach the high value. Sometimes we don't require these type of services, like we don't require reliability, we don't require flow control, congestion control. We are okay with rather than I'll say uh, we are okay with the limited facilities. We are not concerned about the reliability. Two conditions are there: either it's like the applications work very good, and there is a very low chance of packet drop. If there is very low chance of packet drop, we think, okay, the application itself is very secure and reliable, so what's the use of having the TCP there? Rather, let's have the UDP there. And the other thing is, we don't bother about the packet drop. Okay, we are saying, okay, if there is a packet drop also, we can adjust with that, but we can't adjust with the time thing. We want the as fast as possible. We don't want the overhead thing here. So that's the basic difference. So basically, it's short, having no overhead. It's suitable for short messages. No flow control is there. No congestion control is there. In simple words, it's just the wrapper on the IP layer, I can say. So if I say about uh, I'll say no acknowledgement, no connection establishment is there, as the three-way handshaking and all. Nothing is there. No reliability mechanism is there. And no acknowledgement service is there. So that is here. And now coming to header part, we have source port, not much flags and all, nothing. Destination port we are having, where we are starting, where we are ending, what is the length, and a simple checksum is there. Can someone tell me in short what is checksum? Though I'll not elaborate here.
Ma'am, it is just a function which checks the uh, correctness of the data which is being passed.
So it is basically error control, I'll say. It checks that
Yes, ma'am.
this error is basically not about, I'll say, it's not about, it's not any security concern. Like if attacker is attacking, it cannot, it's not for that. It's for like if there are small errors in modulation.
Parity checks
Hmm.
like the having code.
Yes. I think that that will be discussed in the further lectures, having code and everything. I'll come to this checksum also, CRC checksum, error control mechanisms. Also, in the further lectures, I'll not describe. I'll not go in detail here. So let's go ahead. So we have various applications of UDP, where UDP is used. One of the application, very famous application, that is Quick. Can someone explain me about Quick? So DNS and all, BootP, TFTP, SNMP. SNMP we know, DNS. You know about DNS? Anyone?
And domain name server.
What is that? UDP is used for live streaming. Absolutely correct, Aman. It's used for live streaming. Yes. DNS, what's the use of DNS? I think I have explained in previous lectures.
Ma'am, it translates the IP into a particular domain name when going through the network layer.
Yes.
Sorry, I mean transport layer.
So host name into IP address,
Yes, ma'am.
basically. So that's the use of DNS, where we use UDP only, where we want the quick replies as well. If I talk about the like quick application, so if I talk about quick, can you tell me about in short about what is this quick?
Ma'am, it was kind of a protocol mechanism which was set up uh, above the UDP. It will act just like the TCP, but without the overhead of the transport layer. And it was, I think, yeah, it was invented by Google because
Yes.
it has the benefits of the UDP and also some sort of reliability checks, just like the TCP, but
Absolutely correct.
in a short version.
Yes. So basically, we don't need any additional security layer. Encryption is there, and the quick has the security things as well, the reliability things as well. So that's why, it's the application on the UDP. If I talk about HTTP 1.1, HTTP 2, and quick, can someone explain me what were in HTTP 1, HTTP 2, and the benefits of quick over them? Yes, come on, fast. Yes.
What do we have to tell here, ma'am?
What is like what was in HTTP 1.1, how it works, HTTP 2, 2, and then how was like in quick, basically the TCP connection when HTTP 1.1, HTTP 2, and quick, what's the difference between them, how they work, what
Was
was
uh,
feature added?
TC like multiple TCP connections between same client server.
Yes, multiple TCP connections were there, like yes, in the HTTP 1.1. What about HTTP 2?
Here we could like combine them in a single connection and use multiplexer for
Hmm.
like.
Combine them, the same connection was used. Then what was the drawback?
Multiplexing.
Multiplexing, okay. What was the drawback?
So if like say one packet of one connection is lost, then we have to like retransmit packets of all connections involved.
Okay. So basically, if I say that 1 to 10 packets are being transmitted and the fifth is lost, so can I say that 6 to 10 will not arrive until the 5 is retransmitted? Is it like that?
Kind of like basically if one packet of one connection is lost, it like blocks all other packets.
Yes, basically, it's like if one packet is lost, the others cannot be arrived. That's basically called as head of line blocking, HOL. Just telling in short, it's like if one packet is lost, then whole single packet is lost, then the other packets in that stream basically will not be transmitted. The other packets which are following them, that is head of line blocking. That was a disadvantage. Now what about UDP? Yes, here it basically solves this problem. No blocking is there because of the reordering thing, and obviously it's like HTTP 2 only, whereas blocking is basically not there. HOL is basically this problem was solved. And here what was this, like once a connection is established, then we can basically send and the handshake, like once the initial handshake is done, then we can send and receive the data. Unlike TCP, every time we don't have to do the full handshake while sending the data, and we don't have to repeat the handshake. What is the case when we have to repeat this handshake? Only initially we have to do the handshake. We don't have to repeat the handshake. What can be the exceptional case when we have to repeat the handshake? I'm just summarizing it, not going in detail. Yes, anyone? Come on. You got the idea? What do you mean by repeat handshake, not repeating a handshake? Yes? Yes, class? Should I go again with this quick? Or the things are getting cleared?
Ma'am,
That
it is clear.
okay. We don't have to repeat the three-way handshake only
Yes, ma'am.
if the server credentials are changed, because we are also sending the credentials here, because encrypted request is there. Only then only we have to again have the I'll say repeat the handshake in that case. Otherwise, once the handshake is done, then we can basically send the data and receive it, unlike TCP. So this was in ACM SIGCOM paper, as we are doing the studying computer networks only. So I'll say this is the if you are into research, this is one of the renowned, very good conference, A-Star conference. So how many of you are basically in the research part, or all are any one of you? Okay. So if you are into the research part, then this is, or if you are studying computer networks, you should know about the top A-Star conferences also. So this is the best, one of the best, I'll say, top-notch conference in our field of computer networks. So this paper of Quick by Google, it was basically published in ACM SIGCOM. I've also visited the ACM SIGCOM conference. Okay. Let's proceed. Till now, any doubts in transport layer, TCP, UDP part is over. Any doubt, quick part, like security part is already inbuilt there. So that's the advantage the Google has done for us. Encryption is already there. TCP, how TCP is different from UDP. We don't have to do connection establishment and all. Any doubt? I think last time I started with some MCQs, but we haven't covered that part. So let's start with I'll do the MCQs and then we'll switch to the socket programming. Okay. One minute. Wait a minute. I think this was discussed, or it was pending. My screen is visible.
Yes, ma'am.
Was it discussed?
Yes, ma'am.
Okay. I thought something was pending last time. Okay. This delayed acknowledgement part, was it pending or discussed?
It was discussed, ma'am.
I think some questions were left. So let's discuss. I think I have skipped that part. I think some questions were left from this. So
Yes, ma'am.
let's start it again. So what is the main purpose of delayed acknowledgement in TCP? Because we haven't covered some concepts. I thought let's start not go through it. Okay. So please write in the chat with the question number as well as the like 1A, 1B, 1C or 1D. So what is the purpose of delayed acknowledgement in TCP? Let's be fast so that we can go to the socket programming, switch to that. To reduce the number of acknowledgements sent, improving efficiency, to delay packet transmission for congestion control, to wait for senders retransmission before acknowledging, or to improve the reliability. Absolutely correct. To reduce the number of acknowledgements sent. How does Nagel's algorithm improve TCP performance? By delaying acknowledgement, by combining small packets into larger ones before sending, by retransmitting lost packets immediately, by discarding small packets. Absolutely correct. 2B. Which problem does Clark algorithm address? Silly window syndrome, TCP congestion control, packet loss detection, or fast retransmit? Absolutely correct. It's 3A, silly window syndrome. What is the primary cause of silly window syndrome? Retransmission of lost packets, sending small packets unnecessarily, excessive delayed acknowledgement, or buffer overflow at the receiver. Absolutely correct. It's 4th B, small segments unnecessarily. Which TCP timer is used to detect lost packet? Keep alive timer, retransmission timer, persistence timer, or time wait timer? Is it persistence timer or can someone tell me about what is persistence timer? Nilanjan, we are doing 5th question, not 4th.
Sorry, ma'am, typo.
What is the persistence timer? Can someone tell me again? Yes, come on. Come on. Persistence timer was Windows 01.
Ma'am, it will.
It's basically retransmission timer. Okay, I'll come to that again if you'll have doubt. Let's go to the next question. RTO is calculated using which method? Now only we have solved. What about others? Yes, it's 6th B, UWMA. Coming to 7th, Kern's algorithm is used to prevent the retransmission ambiguity problem, increase TCP throughput, detect packet loss, adjust TCP window size. Absolutely correct. What about others? It's prevent the... Yes,
Can
yes.
you explain Kant's algorithm?
Yes. Like we have solved the like okay, we have solved the question in which we have done EWMA. In that we did that. Okay, if suppose I'll show you. I'll not tell you. I'll just show you. Now only we have solved it rather than telling you. Like when we were calculating SRTT, RTT where RTT, what we have said that if there is like retransmission, I don't have to update this RTO. I don't have to update these values because there is retransmission here. So maybe the value might be wrong while calculating this SRTT, because R here, we don't know about what is the calculated R exactly, because there was a retransmission here. So whenever there is retransmission, don't solve it through numerically, only just take the previous RTO and double it. You have joined the class late or you were there?
No, ma'am, I joined late.
Maybe you can see the recorded video as well of
Yes,
this
ma'am.
numerical. So yeah, it will be more clear. If there is a retransmission, don't solve these numerical part. Only take the previous RTO and then multiply it by 2. Maybe for the more clarity, you can go through the recorded.
Okay, ma'am.
Okay. TCP uses which congestion control technique? Simple. It's very simple. Yes, absolutely correct. AIMD. In TCP Tehue, what happens when packet losses detect? Maybe I haven't named it. TCP reset congestion window to 1 MSS and restart the slow start. Absolutely correct. How does TCP Renu improve upon TCP Tehue? Only one has answered. What about others?
Ma'am, I think I have to go through the recordings because I
Yes,
don't
maybe
recollect
you
about
missed.
TCP Tower.
It's nothing else. We have done this fast recovery. I think you were there in the class. We have done this fast recovery. Maybe I haven't named it. I'm sorry for that. The TCP or Tehue means like when three duplicate acknowledgements were sent. That
Oh,
basically part is TCP Tehue. We enter the fast recovery and avoiding the slow start.
okay, okay. Yes, I understood now.
Understood, because I think you were in that part. So basically, we are not entering the slow start phase. That is what we discussed. We just started
Yes,
with
ma'am.
the fast recovery part. What is TCP? What is the purpose of TCP fast retransmit? 11th question. Yes. Absolutely correct. To retransmit lost packets immediately upon receiving three duplicate acknowledgements. In TCP, how is slow start different from congestion avoidance? Yes, come on. Absolutely correct. Slow start increases congestion window exponentially, and then when we enter the congestion avoidance state, we are increasing additively linearly. What is the function of TCP persistence timer? So, yes, what about others? Only two have answered. We have done that TCP persistence timer. We are basically receiving a zero window from the receiver, and that is why we are here having persistence timer to basically keep the connection alive here to prevent the deadlock. That is 13th A. How does TCP handle the time wait state? I think I have missed that part. Okay, it was simple. I think we haven't done about time wait. It's basically 2 into. It's basically the answer is A, 14th A. It waits 2 into maximum segment lifetime before closing the connection. It's another type of timer. I think I have told, but at that time I wasn't audible. Okay, let's go to the socket programming part. Okay. I don't think so we can cover today because we have to do with the okay. So or I'll say socket programming. So we have transport layer, then we have network layer, data link layer, physical layer. This is the hardware part, and this is the kernel space. And then we have the physical layer, or the, I'll say, the user space is there. This all is the kernel space, and then we have the user space here. And sorry, this is the kernel space. And application part, sorry, application layer, not physical. So application presentation and all session. So if I talk about, if I have to interact with I have to do the interaction between the kernel space and the hardware part, that is done using the socket programming by the APIs call, system call, and all. That is done by the socket programming, the interaction between the kernel space as well as the hardware part. I'll not repeat again what are IP addresses, what are ports. I hope so that part is clear. Now, what is the socket? That thing also we have discussed. Still, what are sockets? As we have discussed in the previous classes also, it's a logical connection from one process to another, from one machine, from one machine, I'll say, to another machine. The connections which is from one process to, or I'll say, one machine, basically this kernel, and as we have done the interaction. Now the main part is the system calls. Logical binding and all we have discussed about that. I'll skip that part, just coming to the system calls. That's very important thing. Now coming to the first system call, that is in the server, which is, please here, like, be attentive now, because this same thing we'll use in programming. So it's very important part. So let's try to understand each and every system call very carefully, like understand it very properly. So can you tell me what is this socket doing? What is the socket API? What is the socket system call? What is it doing? This is a system call in the server side. What is this API or system call doing? Yes. Anyone? Till now, I haven't taught anything. That was just the interaction, how just for the communication part between the hardware and kernel sockets. Now we have a set of system calls. That is the main important part. When I have to do the communication between the server and clients, a set of system calls are used. First system call is socket. Can someone tell me what is socket system call?
Ma'am, when we take port number along with IP address.
Okay. So
then,
so
for specific application, suppose we want to go for.
Okay. And someone has written socket creates a way to create a work on logical pipe. Yes. So basically, socket is, if I have to create a, as you have said, that a logical pipe, we have to start a socket, we have to open, I'll say, opening of a logical pipe. There, as I told, that there is a logical pipe among the two devices. I have to open it. I'll come to that, the address and port and everything. Don't worry. So we use the socket system. So, rather than explaining each and every, I'll go in detail first about the socket. So if I talk about socket, we'll use it in programming as well. Let's see what are its parameters. So basically, if I have to open a logical pipe at the end of the server calls the socket. Now, it has domain, type, these parameters, 3 parameters are there. What we are doing, we are creating a socket. We are creating a logical pipe. It has 3 parameters. First parameter is domain. Can someone tell me what is domain? Yes, can someone tell me what is domain?
Ma'am, it defines the client side.
Yes, defines the client side. Okay, anyone else? What is domain? Basically, okay, yes. Someone was speaking. Okay, it's basically what is the communication domain, how we are doing the communication, which protocol we are using for the communication. That is basically domain.
Ma'am, it has a
Yes. Come on, at least try. Yes. Okay, so basically it's communication protocol family, I'll say.
yes, ma'am.
Yes. So like IPv4, though we haven't discussed about it, IPv6, you might have heard about these protocols. We'll come and discuss about this in network layer. I'll not describe, I'll just say this is a communication protocol, which is basically, here we'll write whichever protocol we'll use. So if I have to use, suppose IPv4, this is a type of network layer protocol, and I'll not tell about the value, okay, or I'll not tell about the value here. This is the protocol. So AFNI, what does it mean? If I have to use IPv4, I'll here write AFINET. That is the domain. That is the name which is given. Basically, if I'm using, if I have to mention that I am using IPv4, I have to write AFINET. Similarly, if I have to use IPv6, I have to write AF. That's basically how I'm representing them. INET, sorry, INET6. And suppose I have to do local or inter-process communication, basically within that system. So that's the domain. So suppose I have to do Bluetooth. Through Bluetooth, the communication is there. Like how the communication is happening, which protocol. If I'm doing through Bluetooth, the domain is this. Simply what domain means, if I'm using Bluetooth, what I have to write here in the domain. And now coming to type. I hope so. This domain is clear. What is the domain? What is the uh, a protocol is used for the communication part.
Yes, ma'am.
So now, what is the type?
Ma'am, type is used for defining the type of the socket.
Yes, absolutely correct. So if I'm using type is basically what is the type of the socket. If I'm using TCP or UDP protocol for the transport layer. If suppose I'm using the TCP, I'll write here soft stream. If I'm using here and the type, if I'm using here UDP, I'll write here data, basically soft datagram, as we call it as datagram only in the UDP part. Now the protocol, what protocol is basically used here. If I talk about the protocol, TCP or UDP, that's the same only. And if suppose protocol, it's written 0 here, which means it will take automatically. Can you tell me how automatically what it will take? Any idea about that? Yes?
No, ma'am.
Okay. Suppose I'm here writing sock stream, then the protocol itself will be TCP default. It will take TCP because it's sock stream. The type is, if its datagram is transferred, we know that UDP.
UDP.
Here we mentioned that packets are called datagram here. So here automatically it will select to the default protocol if I'm mentioning 0 here. So this was the socket part, the socket system. We will do in programming part. We'll write this socket, we'll write this domain type and protocol. When we'll start the program, first we'll establish a socket, a logical pipe. Now coming to bind. I'll go with the bind, and I think I'll close the class because I'm unable to speak as well. I'm not well.
Okay, ma'am.
Yes, and I thought that I'll complete the programming part also today, but it's not possible. Okay, can someone tell me about bind?
Ma'am, it assigns a address to the socket, and then it will help to bind to the server as a client.
Mm-hmm. So basically, as someone told me about socket, in the socket part, someone told me that we'll have the port number and socket. Here comes that answer. As you have told, we'll associate the socket with a particular specific IP as well as the port number. That is basically the bind here. What we are doing, we are binding with the particular port number as well as the IP address, that socket here. If I talk about bind, the bind here, it has the parameters socket ID, address port, as well as the size. So what it is doing, it is reserving the port for a particular socket. Socket ID, that is obviously the identifier. Address port, it's the IP address and the port of the machine, port number of the particular I'll say the application which is used, and IP address of the particular machine. And size is obviously the size of the socket, address structure. Any doubt?
No, ma'am.
We'll discuss the other parts, the other things, other system calls in the next class, and the programming as well for both TCP as well as UDP we'll do in the next class. I hope so. Today's lecture was fine. Any feedback?
It was good.
What about others? Okay, Aman, I read now only socket creates. Good, okay. Thank you so much for all the thumbs ups. I hope so. You got the lecture. I'm sorry for leaving it early. And I'll try to cover the network layer as well as, I don't think so the full network layer will be completed, because the socket programming itself will take a lot of time, I think. Though I have written a program earlier only. I'll just explain it by writing the comments with each of the lines so that you should understand. The same system calls will be written, the same thing will be written, whatever I'll explain in the theory. The socket is called, and then a logical pipe is creating, then binding and everything. The same thing is written in the program, nothing extra. Only the C programming we'll do in the C programming itself. Only the syntax and all is different. Otherwise, the same thing is there. UDP, it will be the simple one. TCP, we'll have the 3-way handshake. And then we'll come with the parallel also. Okay, in this iterative server and then the parallel server also, in which we'll have one server, whereas multiple clients are basically connecting to it. That also we'll do. Thank you, class. I'll again write whosoever has attended late, or whosoever has want to see the last lectures. This is the YouTube channel name. So you can go through it.
Thank you, ma'am.
Thank you, class.